But there's a question about, I think it was Arfken and Weber 1413. Let's call it A and W. And I think it was mostly because this was a little bit of a vaguely worded question. So the question was if, so I have a function f of x and it's real. What can I say about its exponential? Let's get this out of the way. Which is to say the c sub n. And you can go pretty far with this, to be honest, if you really wanted to like kind of get down on Euler's formula. But the minimal thing you can say is this. And honestly, mostly this is like what style of proof would something like this be looking for. Honestly, most of the Fourier theorem series or transform properties that you guys will be asked to prove or look into, it kind of boils down to just like write down the Fourier formula. So we have f of x, and it's got a Fourier expansion. So in the exponential form of that, it's all possible integers, positive and negative. And there are these coefficients c, n, which could be complex valued, and then e to the I n x. And then what we're saying is this is equal to its complex conjugate, right? So when we're talking about things that are inherently complex, is real means the thing equals its complex conjugate. So I think this is the easiest and most fruitful way of writing down, you know, anytime somebody says like, well, if I have some number c and c is, you know, real, what that means is c equals c star, it equals its complex conjugate. It seems like a little bit of a clunky way of writing things, but, you know, you'll see that this, you know, this turns it into like basically a two-liner, because what is the complex conjugate of f of x? Well, I just complex conjugate everything that's complex, and so that becomes cn star, its complex conjugate. What's the complex conjugate of the ei and x piece? That's just minus in front, okay? And so now I have sum over all the Fourier coefficients, n and z, cn e I n x, and then cn and z, cn star e minus I n x. So if two series are equal, you can't immediately say that they're term by term equals. So let's say that I had one series that went 2 plus 0 plus 2 plus 0 plus 2 plus 0. And I had another one that was like 1 plus 1 plus 1 plus 1. The series themselves, yeah, fine, it's infinity, but the series themselves are equal, but the terms themselves aren't equal. So it's not immediately obvious. You actually have to work for this to say like, wait a minute, I know that these are term by term equals because this thing is a function of x. And we'll make this argument a number of times, is that, look, there's a coefficient, the cn, and then there's a function of x. If this is true for every single value of x, then it must be true on a term by term basis. So only because there's this like function of x, e to the I n x there, then I can start equating terms. And it's not true that this e I n x equals this e to the minus I n x term. What is true is that if I put a minus sign in front of here, I fish through the entire series and I find this one, the one where n is negative this n, then I can say they're equal. So equating individual terms, so that's so equating the exponential terms, what I get is, okay, I want a minus sign in front of this, so I have to say e to the we'll do it really clearly, e to the I minus nx. So I fished through this entire infinite series and I found where the n on the left-hand side is equal to the minus n on the right-hand side. And now what's true is now I can term by term equate these because this is the exact same thing. It's just I have the minus sign inside or outside. So at the end of the day, if I have a real function, what's true about the Fourier coefficients is that the complex conjugate, so they're not real, right? Because the e to the I nx is also complex. But what's true is that the complex conjugate of the nth term is equal to the negative nth term. So in some sense, the series folds over. And at least one person, bless your heart, went further and said, aha, what I see is that because I'll say you can keep going. It gets, this doesn't really help as much as this, because you end up with a somewhat messy expression. But because e to the I nx, and we'll put the minus on there because it's up there, is equal to, by Euler's formula, cosine nx minus, so cosine is even, so that minus doesn't do anything, but sine is odd, so the minus comes out front. E to the I, sorry, minus I sine nx. Then what I have is, with this condition and this condition, I can actually kind of fold the series in half, and I can end up with a series that looks like this, just n in the positive numbers of some yucky coefficient, e to the I nx. But this, is work. Okay. So any questions about that? I forget who asked. Yeah, I think it was mostly the question itself. What you guys are probably more used to is a question that says, like, prove this specific thing, instead of like, hey, what can you say about these Fourier coefficients? They're pretty crazy. So maybe it was the open-endedness of the question itself. Good. Okay, so we are in tensors. And I want to start with just like a warm-up. And let's say that we have a stress tensor. On a small rectangular surface. And the small just means, it's not big enough that it's heterogeneous, like it's the same stuff all the way through. So, and this is just the formula, so I'm not going to coach you guys too much on this, is that F equals T D, or maybe delta if the thing's like kind of, not infinitesimally small, sigma, right? So what this does is you tell me the surface and I tell you the force on that surface. And this is something that civil engineers, this isn't really exotic to them. This is probably their bread and butter, or material scientists for that matter. As a side note, I'll work it in here somewhere, but I realized why we don't talk about elasticity. It's because the elasticity relates stresses to strains. And so we'll talk about the size of it in tensor talk today, which is pretty crazy. And so as far as this problem goes, let's just put some numbers on this. And I will first ask you what the units are. So this is a thing that the most generic thing that turns a vector into a vector is a second rank tensor. And we'll not kill ourselves here. So let's do 1, 2, 3, 2, 2, 0. And let's not go super crazy with it. Let's make it symmetric, so it's not like a super funky material. And ask two things. So first, find the SI units of T. And B, let's find the force and I don't want to lead too much. Force, pressure. on the right-hand surface. Let's do left, actually. Okay, so we can talk through these before getting numbers. What are the SI units of the stress tensor? So what are the SI units of the left-hand side of this equation, which in some implicit way kind of defines the stress tensor?
Newtons.
Yeah, just plain old ordinary newtons. And then what about this d sigma or delta sigma? What are the units of that?
Meter squared.
Yep, meter squared. So the units of the stress tensor are newtons per meter squared. Okay, so now we can kind of resolve this. What would you need to tell me if you had, so if I was looking for the pressure itself, I kind of already have it because that's the units of pressure. This is in pascals. So if I want the pressure on the left side of the cube, all I have to do is specify the direction of the left side of the cube and the units already work out. If I wanted the force on the left side of the cube, what would I have to also furnish?
The actual size of the area.
Yeah, so the actual area. So let's just say like a 1 centimeter squared face. Okay, just to throw a little bit of powers of 10 curveball at you guys. Okay, so this is in SI units. We now know that this is in newtons per meter squared. So the stress tensor's units are pascals, essentially. And then we have 1 centimeter by 1 centimeter area, the left side of this. What you guys got to do is figure out the direction then. And this is the usual orientation, so we'll call this X, Y, Z. And then this is X, Y, and Z columns. So no trickiness with like the definitions of the directions. And now you can give me a number. So you guys like a minute to do that. Okay, so what this kind of boils down to is what is the, or in this case we want an actual force, so what is delta sigma? So what is this column vector here? So it's got two properties I care about. It is a vector. I need its magnitude and I need its direction. So let's find direction first. Which way does this area vector point for the left face? So the good news is there's no ambiguity because this is a closed surface, so it points out. And so that makes it in the negative y direction. And then its magnitude is just, we're in SI units, we got to keep SI units. 0.01 times 0.01 is 1 times 10 to the minus 4th. So this is the negative y direction, so that's minus 1 e minus 4, fitting that in there awkwardly, meters squared, because we converted to SI. Okay, so this is the neat thing that happens and never happened to you guys in just plain old ordinary 1210 mechanics, is when I multiply this vector by this tensor, what I get is forces that have components in which directions, actually. So I will go through and I will get an x component and a y component, no z component. I should have put a z in there just because it would be easier to draw, but whatever. So I get minus 2 times 10 to the minus 4th. Same thing there, minus 2 times 10 to the minus 4th. 0 newtons. And what this means is that even though the surface itself, the normal to that points in this direction, the force doesn't necessarily need to. So, and that's, you can think about just putting your hand on a book and you can press downwards and you can try to slide it across the table. It's absolutely true that we can have forces and stresses that do not necessarily always point normal. And you need a tensor to do that. So this is F on the left-hand side. And then if you picked a different surface, you would have a different force and so on and so forth. So that's the thing that tensors let us do. They actually let us express a lot more robust physics. So basically, anytime you have vector A and vector B in physics, the most generic way of relating one to the other is a tensor. Right? In fact, we'll even be able to express the exotic thing, a cross product, as sort of a tensor. So it doesn't transform properly, so it's not quite a tensor. But any questions about that? Okay, so we've got some bookkeeping to do before moving on into really exciting tensor stuff. And I think ending a discussion of tensors with just the Levi-Chitiva symbol is kind of boring. So I'll make you guys in the homework calculate some Christoffel symbols. And if you can do that, you basically like almost all the way to general relativity, at least with the math, which is pretty cool. But first, we got to go back and talk about something that you never really had to worry about too much in Cartesian. So the sort of subtlety is that, let's say that I have a vector, and you now know that the vector is a geometric object. It lives in space. It's got its own life independent of the coordinates and we express it. But sometimes you choose to express it in coordinates. And that kind of goes like this. K is a summation from 1 to 3 of vk ek hat. Right? So I've got unit vectors, 3 of them, and I've got components, 3 of them, and I sum over them. So first, just, eventually where we're going is notation, Einstein notation. Just look at this and realize that if this were like, computer code, you'd be like, there's got to be a more elegant way of writing that. So there's all these repeated Ks, and it just looks kind of clunky. But there's something else going on, is that the V's, the components, and the unit vectors actually act differently. So a subtlety that we probably never talked about before in physics is that the components and the unit vectors act differently. Under transformations, which could include me just like scaling stuff. So we'll just say under transformations. And the easiest way of seeing that is if I just go from like meters to centimeters. Well, so I have a vector and I used to measure it in meters, and now I measure it in centimeters. What happens to the magnitude of that vector? Does it go up, go down, or stay the same? So all of a sudden I'm measuring the VK in meters, then I'm going to have like more centimeters than I would have in meters. So let's say that this goes up, right? We just, for example, go from meters to centimeters. So the size of each VK increases. Okay, but what is true about the size of a unit vector in meters versus centimeters, which is to say like the size of the thing itself. So this would actually go down. And in some sense, because the vector itself is invariant under the coordinates that I choose, I have this geometric invariant thing. If the components increase in some coordinate system, the unit vectors need to decrease. So in fact, these things transform in opposite ways. And there's a special name for that. So we say covariant if you transform with the unit vectors, and contravariant if we transform against them. So we have two definitions. So we say a mathematical object and the contra, you can remember like against the unit vectors. So for us, we would say that the individual components are contravariant, and the unit vectors themselves, you know, in this definition, kind of by definition, are covariant. And this is also that the geometric thing itself, like if they both increase, then the geometric object itself would not be invariant under coordinate transformations. Okay, so we're going to introduce some notation, kind of double notation. We're going to put the indices of contravariant things upstairs. So notation is going to be contravariant indices upstairs. So I'm going to write henceforth because that sounds like a proclamation and really serious. So henceforth, contravariant indices are upstairs. So this is no longer the right way of writing this vector. We now write it v up k. So these are the components, and covariant indices are downstairs. And as my first GR professor told me, he had trouble remembering this. So the mnemonic is co is low, that's all you need to know. So covariant goes downstairs. Okay, so what? You're just introducing more rules into my already complicated life. So here's so what, is that once you have a rule for contravariant and covariant, then this sum that occurs up here can be considered to be redundant. So we kind of started this with me just asking you guys, doesn't this look kind of silly, this like all this repeated stuff? So we will now introduce, you guys okay with the definitions? Okay. So we'll now introduce Einstein summation notation. So this is also, you know, Einstein has his name on enough things, and I think the mathematicians maybe got a little bit annoyed with it. So you probably see this more in mathematics circles, but it's also called implied summation notation, for the reason that if you see a correct format of repeated indices, it's assumed that we're summing them. Okay, so now I have my vector v, and it's a real geometric thing. It lives in space. I'm just going to write it like this. So vk, ek. So because I have a repeated index, so two things I have to check for is k is a repeated index. And 1k is contravariant. 1 is covariant. It's assumed that there's a ghostly sum k goes through all the things that k is able to go through. So in special and general relativity, k usually goes from 0 to 3, and just normal 3D stuff from 1 to 3. Okay. And in computer vision, from 1 to some large power of 2 in all likelihood. Yes, if you guys end up doing any machine learning stuff on, actually I think all the major platforms use it. So any machine learning stuff, they use tensors because that's exactly what they are. Okay, so now we can rewrite our couple of examples. See if you guys can do this. Write the stress tensor equation that we started today with in Einstein notation, or implied summation notation. Is anybody happy with their answer? So this is what we probably all agree on, is that the formula look like this. Just use the delta sigma. So the question is, what indices should I write and where should I write them? Okay, so what is it that we want out? And what did we put in? We put in vector components. So the index for vector components should be where, upstairs or downstairs? Because we got vector components, we go upstairs. And we got vector components out, so upstairs too. We're gonna sum over k, so where does the k show up in the stress tensor if we're gonna use Einstein notation? So if we're gonna sum, it's gotta be that. And finally, if we want a contravariant transforming thing, i.e. the components of the force, these got to match. So this is, and the J should be in front of the K. So this is how you would write the actual component formula for determining the components of force from a surface given a stress tensor. And there's an implied summation over K. Okay, it's a little bit clunky at first, but then, you know, if you get to something like the field equations of general relativity, you're so grateful for summation notation. Okay, the other example we had was, I think we did inertia and the inertia tensor. And it looked like this. Come up with some components and put them down, make sure that you can, you know where they go. And let's say that we want to sum over, let's just call this I, right? And I know that's upstairs because those are components of a vector. Do you guys get something that looked like this? I see that really peculiar face where you're like, I'm wrong, but you're like, I don't really want to say anything for one reason or another. What's slightly wrong about this?
The J should be on the top of I.
Exactly. Yeah. So that should be a superscript, or what you can now call it is, most precisely, is you can say the J index should be contravariant. And there's an implied sum over I here. Okay. And what this is mimicking in some sense is this is Lx, Ly, Lz. This is what you should see in your head. I, X, X, I, X, Y, I, X, Z, dot, 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 I, Z, Z. Of omega X, omega Y, omega Z. So what this is saying is I am summing over this index, and that's the act of taking this column vector, flipping it over, multiplying it like a dot product here, and then using that to produce that, using this kind of dot product to produce that. So you do sum over 1, 2, 3, right, to get each one of these. Okay, so any questions about that? I'll do 2 more things, and then we'll see how we can transform vectors. Actually, it turns out to be pretty easy. Or sorry, transform tensors generically. We just need to figure out a basis for them. So we'll do this. It's the lowest rated game show ever. I'm just using mu as an index. Okay, you can either tell me like the type of mathematical object it is, or you can tell me what this actually is in terms of stuff that we talked about probably on like day 2 or something like that. So this is now the way of writing something that we've done a whole bunch of times. Got B contravariant mu, and then A covariant mu. So what does that mean about the components of A and B?
They're vector components then?
And then because I got one upstairs and one downstairs, what am I doing when, for instance, so usually the tradition is you save the Greek letters for space-time, so hopefully it doesn't complicate things too much. So this is this is A0 times A0, A1 times A1, A2 times A2, and there's an implied summation. So this is really kind of unpacked to this, the way that we would usually write stuff. What is that? And don't let the 0 confuse you. It's just, could be 1 to 3. Yeah, this is the dot product. So this is the dot product. So from here on out, you can say the dot product of the vectors v and t or something like that looks like this. That's what dot product means. Okay, so sort of a warm-up. This one's a little bit tougher. I have a second-ranked tensor, and I have one upstairs index, one downstairs index, but they're the same index. So think about what this is really telling you in terms of Einstein summation, and what is this? So usually Latin indices are reserved for just space. So k goes from 1 to 3. And this would be, in the usual notation, t11, or sorry, t11 plus t22 plus t33. So what is that? We haven't talked about it much here, but probably in linear algebra you saw it. What's the sum of all of the diagonal components of a matrix?
Determinant?
So, say again?
The determinant, 'cause that's like the main diagonal added.
Yeah, part of the determinant shows up there. So we'll get to determinant. You need to come up with all the permutations. But the first thing you take in the determinant is just along the diagonal, which is the trace. And because this is a tensor, we'll call it trace of the tensor. But this would be like t11 plus t22 plus t33. So just these guys added up along there. Okay, and I'll do this because this is super brain teaser. I'm going to say that this is a dot product and I'm wrong. Why am I wrong? Do I sum over anything in this? I've got A downstairs covariant mu and B upstairs contravariant nu. So there is no Einstein summation because we do not have a repeated index. So this is what's called an outer product. And an outer product is two vectors go in, and in fact, what we're going to get out of this is a rank 2 tensor. So let's do an example of this because this is where we're going to get basis vectors. Just no summation. So this is just, what is that? And let me give you guys a handle on what these things kind of are. So A mu, this is something like a basis vector because we're downstairs. And let me just like come up with some numbers so we can get a real example. Call it 1, 0, minus 2, I don't know. And then B nu, in order to distinguish this, this is really just notation. We can call this a row vector. Like if one of these is a column vector, one of these is a row vector, especially for low dimensional things in quantum mechanics, you'll do this a lot. So denoting, just notation, denoting covariant things as column vectors and contravariant things as row vectors is perfectly fine because this gets across the point of what this is. We have no summation. So what this is how many possibilities are there for A mu, B nu. So mu can go from 1 to 3, or 0 to 3 if we're doing special relativity, which I'm not right here, it's 3. Mu can go from 1 to 3, nu can go from 1 to 3. They're not the same index generically. So how many possibilities are there? Well, 3 times 3, 9. So for instance, A1, B1 would be 1 times 4, right? So the 1, 1 component of this. So I take the first element of A mu and the first element of B nu. So that's 1 times 4 is 4. And then I take for the 1, 2 element, I take the first element of A mu and the second element of B mu. That's 1 times 1, 1, and then 1. And then I can go a little bit more quickly. The second row is the second element of the column vector and the row vector B mu. So that's 0 times this whole thing, right? So 0 times this whole thing is the second row if I track the indices. So that's pretty easy to do. That's 0, 0, 0. And then I get the third row times whoa, this, I swear. So that's minus 2 times 4 is 8, and then minus 2, minus 2. So if these things transform right because I said so, then so does this. So voila, what we've done is we've made a tensor. So the outer product makes tensors. And in fact, what we can do is, in the same way that we expressed, really what a vector is the following thing. Does anybody have any questions about where these numbers came from? Or how to compute an outer product? Have you guys seen that before at any point in linear? Yeah, maybe.
I think so.
Yeah, all this stuff becomes, in quantum mechanics, and GR is kind of your bread and butter when you get into like spin and things like that. Okay. So now we know how to make a tensor. So before, what we were doing, and you do this a lot, is you confuse the components of a vector with a vector. And that's why we started basically this entire quarter with, trying to beat you guys up a little bit about this, is that we now know that this is true. Cool Einstein summation way of doing it, regardless of the units and regardless of the particular basis that you choose, is that what we can do is, go online and you can find some people trying to visualize tensors with like weird explodable Rubik's cubes and stuff like that. But let me just say there's a tensor out there, okay? So I'm not going to try to draw it, especially on a 2D thingy. But there's, and my claim is that this is really what a tensor is in some sense, is that a tensor is a collection of components, kj, and then we can have the outer product of basis vectors. So this is the symbol for outer product. And if I'm matching indices, and this is a little bit redundant because I already have the covariant and contravariant K and J on these. So it's a bit redundant to put the outer product on there, but really reminding you guys, this is an outer product. So if I have a rank 1 tensor, which is to say a vector, I have 1 unit vector. If I have a rank 2 tensor, then I have 2 unit vectors. If I have a rank n tensor, then I could take an outer product of n unit vectors, which would be like pretty grubby. But the way this works is, for example, just in, Cartesian easy coordinates where we have, e to the k is, I don't know, just call it e2 is 0, 1, 0, and e hat 1 is 1, 0, 0, like standard basis. Then e2 outer product with e1, what's that going to look like? It's going to be a basis, or sorry, it's going to be a tensor, rank 2 tensor. Second row, so this is going to have well, let me actually write it in both ways. So let me write our cooler way of doing this. So this is 2, 1, for instance, right? So this is the column vector, the 1, and then 2 is the row vector. So we have a row that's 0, 1, 0, and a column that's 1, 0, 0. And so what I get, this is just notation, but these are the same thing. So what I get is something that looks like this. which is to say it's 0 everywhere aside from the 2, 1 element. And likewise, if, for instance, I took, 3, 2 outer product, which just notation is this, it's going to have the 3, 2 space be 1, and then everything else is 0. So this is a basis of tensors in the sense that if you give me any box of 9 numbers, I can express it with a combination of these things. And then if they're vectors themselves, then they transform correctly. Okay, so generically, what I have is this. So this is the most generic expression for a tensor. So a tensor is Tkj E K E J. And you can play games with indices. You can raise them and lower them. We're not quite there yet, so I'll just write it like this for now. So there are 9 numbers, and then there's a basis for them. And then in Einstein summation, the sum over the k and the j are implied. Okay, well, so what? Okay, so this now lets us transform tensors properly. So now we know how to transform tensors. Because we already know how to transform vectors, i.e. the unit vectors. So let's say we have a new basis. And we go all the way back to, is it like day 1 or something like that? Is I just have I have a transformation matrix AKJ, so AKA the direction cosines or something like that. And I want to go from one basis vector to another. So EK hat, and then A. Now we can Einstein summation stuff. Because of the properties of the transformation matrix, unit vector goes in, unit vector comes out. This is how we transform basis vectors. And to be honest, I should have one index up and one down there. Kind of thinking in Cartesian. Call it KJ. So if we want to transform a tensor, all we have to do is supply one of those for every single index. Right? So ... if I have an nth rank tensor, the components would transform like this. So this is sort of a notational no-no to mix Greek and Latin indices, but I'm going to do it because it just makes this expression look really nice. Let's say I have a 4th rank tensor, alpha, beta, delta, gamma. And it used to be a 4th rank tensor in a different basis, so IJKL. And, whoops. Yeah. So just like vector components, I want these to be contravariant. So I need to transform 4 indices fourth rank tensor would have 4 sets of these things. First rank tensor would have 1, just the one basis element. I just need 4 copies of the rotation matrix, and they need to do what I need them to do. So I need to get rid of an L downstairs, so I have an L downstairs, and then that'll make a gamma upstairs, 4th index. And then I want to get rid of this K, so I need, whoops, that's upstairs. K upstairs gets summed over, and then I produce a delta upstairs. Get rid of this J downstairs, I make a beta upstairs, and then finally I get rid of this I downstairs, and I make an alpha upstairs. So don't worry, you won't have to do this like on a daily basis. This is how I would transform a tensor, and this is what it means to say the thing is a tensor. So a tensor is an object that transforms like this. So if you change coordinate systems, if the components do this, then it's a tensor. Okay, so at this point, this should seem like pretty abstract and just like kind of a silly game where you can look at Einstein summations and say like, that's okay. This is, you know, for instance, this is going to end up as like a 4th rank tensor or 2nd rank tensor. We'll do one example. And then at the end of this, we'll talk about the raising and lowering of indices. And I think that makes everything a lot more clear as to what this actually means. So there's a reason you guys have made it through most of your lives so far without ever seeing this probably, is because for Cartesian coordinates, it like is not important, right? It's only when we get to funny metric functions. Okay, so any questions about this? And we'll actually try to do an example. Okay, 2 of these and you've earned the right to just kind of say like, yeah, I know how I could do this in principle. So let's pick on a stress tensor again. And we'll say stress tensor is given by, we now know it's newtons per meter squared. Still going to give you guys like isotropic materials because it's freaky to think about not isotropic materials. So this is a stress tensor, and it's given to you in some basis, right? Clearly, if I rotate the basis, you know, for instance, the peculiar behavior of the x and y axes is going to be rotated into some new basis. Like the physics should not depend on your choice of coordinates. So what I want is to find which is to say, excuse me, casually find the tensor itself, find T. And we want to find the value of the tensor, which is say its components, in a new basis that's this thing but rotated around the z-axis by 90 degrees. Okay, so what is it that I need to do this? And then we just come up with, you know, coordinate matching and how this actually works.
You need a transformation matrix.
Yeah. Okay, what is the transformation matrix? Okay, how about this? Pi over 2, 90 degrees should be easy. I drew the x, y, z coordinates. You guys draw the rotated coordinate system. And then what should be true is just by looking at it, we should be able to figure out what this transformation matrix looks like. So is there kind of a nice way of describing what this is? So I grab the z-axis and I spin it by pi over 2 degrees, pi over 2 radians. What does the x-axis turn into?
It would be the negative y-axis now.
So we want to do right-handed. So it becomes, you're right, it's the y-axis, but if we go in the positive direction by pi over 2, it becomes the positive y-axis.
Oh,
What is the y-axis? Yeah. What does the y-axis turn into?
it would be the negative x.
Yes. Y-axis turns into the negative x-axis, and what does the z-axis turn into?
Z.
Yeah, the z-axis. So just by looking at this, I can write down what this thing does. So our transformation matrix, z comes in, z goes out, so z is unchanged. And what I'm doing is I'm turning the x-axis, the old x-axis, into the new y-axis. So if I put in the old x-axis, 1, 0, 0, I get out y, that's good. And then the y-axis turns into the negative x-axis. So this is our rotation matrix. Okay, in even just rotated, excuse me, even just rotated in rectangular coordinates, the upstairs downstairs thing doesn't mean anything yet. So when we get to curvilinear coordinates, we have to worry about what it means to take a index and take it from upstairs to downstairs. But for now, I'll put them where I need to put them. Okay, so this is A. Now what I want you guys to do is fill in this equation, and there's a little bit of hint in the white space. And if you put indices on it in Einstein summation notation, that's awesome. You know what you're doing, and the rest would just be like crunching through some kind of grubby looking mechanics. So I'll give you guys a minute to do that. See if you can fill out the Einstein summation notation formula for how I turn tensor components expressed in old coordinate system to new coordinate system. Okay. Anybody happy with their naming and placing of indices? So first question is, without any indices whatsoever, T prime, the tensor expressed in the new coordinate system, is equal to what? And kind of generically, like, what's the right way of transforming a rank 2 tensor, given that I have a transformation matrix A? So, and this is why it, is probably worth going into the pedantry of the outer product and how we actually make a basis for tensor functions. Because the thing is if I do this, I have a 3 by 3 matrix in the form of T, and I have a 3 by 3 matrix in the form of A. This has the right shape, right? T prime equals AT has the right shape. I'm going to get out a 3 by 3 matrix. Is that right? No, so in essence, what I've done now is I've just transformed one of the two sets of basis functions or basis vectors. So this is the right formula. So every index gets its own transformation. And if I want to put on some indices just to make this kind of look kosher, let's call this kj. And then we got to get rid of j, and we'll turn it into I. So j downstairs, I upstairs. Don't worry about how I get from upstairs to downstairs yet. We just know this is in the right form because we made it in the right form. And then k, let's turn that into an L, I don't know. And then what I end up with is TLI. And I'm just gonna kind of write this, and then hopefully I will assume what I have in notes is correct. But I want to make a point about what comes out of this final calculation. Okay, so two multiplications happen, and what you get is something that looks like this. Okay, it kind of smells right. Like all we did was flip some indices, so we shouldn't get anything bigger or smaller. No sines and cosines. Smearing the indices into other indices, we just flip them. So what I might expect if I didn't know about how to transform things properly with transformation matrices and a rank 2 tensor is I might have just looked at this and said, look, here's the deal is I have x going into y and y going into minus x. So why don't I just flip the x and y's and that does nothing because this is a symmetric tensor over those indices. And then I will also, anything with an x on it, I will flip its sign. So I would completely get that wrong. I mean, not completely, they're close, but if you're building a bridge and this is a stress tensor, I really want you to get it right. So just like a geometric argument of yeah, I should flip some stuff, you'd probably get it wrong because there's some subtleties in how the basis vectors transform. Okay, so this is the right way of doing things. Any questions about that?
I guess earlier when you were talking about what object is this, we were looking at I think a tensor that had indices on the bottom and the top, and you said that was a trace. How should we think about those indices that are on the transformation matrices? Because it seems like we just multiply, and the indices don't really end up mattering.
Yeah, that's a great question because this is one of the annoying subtleties of Einstein summation notation that at first pass when you're just trying to grok all this stuff, you might miss. There is a huge difference in between this and this. And in just the lexicography of writing this, they look so similar, but this is a non-repeated index. So that means that this is a box of d squared, where that's the dimension of my space numbers. Okay. So in this case, a 3 by 3. This, because it's got a repeated index, what this is the sum as k goes from 1 to 3 of a kk, or kk, upstairs, downstairs. And so for this would be 1 plus 0 equals 1. And it's not physics, it's not math, it's just a way of writing stuff. So this is a summation convention. But the thing in our example was the really spooky trace. So because that's a repeated index, ai upstairs, ai downstairs, that's implied summation. And so it's just the sum of the diagonal elements, whereas this, there's no sum because there's no repetition. Yeah, good, because that'll happen again. This shows up a lot, actually. Okay, so let's